Hey look, it's Paper Cam, Wave of the Future. This is our second video in the Abstract Algebra for Kids series. Actually, it's the first true one. The previous one was just the introduction, so we're just going to dive in here. So, the first thing to think about in Abstract Algebra is operations. And an operation is basically a rule where if you have an ordered pair of things, which are an element of some collection or set of things, then the operation assigns to that ordered pair exactly one other ordered pair. And there are some stipulations there. So I think just to have an example, so we're not hitting an invisible tennis ball back and forth and not knowing what we're talking about, let's talk about rock, paper, scissors. So, rock, paper, scissors. This is our set. Actually, I'm going to color in the rock. So, rock, paper, scissors. So, we have a set of three things. This is our collection. And if I have an ordered pair, I have two of them, right? And then I assign them exactly one thing from this set. So let us do that, and we're going to just say the winner. The operation that we're talking about here is winner, right? So if rock and paper, then that goes to the winner, which is paper. Now here are the stipulations or rules you would have to abide by if you're really defining this as an operation. The important aspects of the definition are that it's defined for every single pair, right? So imagine if rock, paper, scissors, there was a situation that came up where we'd said scissors and rock, and it was like, oh, we don't have a rule for this pair. Then this can't be an operation, because in order to be an operation, there has to be a defined result or thing that the pair maps onto for every single pair in the set. Otherwise, it's not an operation. In this case, it is rock and scissors. We get rock. Okay. So then, another rule or feature of operations. I kind of don't like the word rule. This is just something that was decided when they defined operations, is that the thing that it maps to must be uniquely defined. So we can't have something like this. Or actually, let's put scissors. That would make more sense. Like, well, if it's rock and scissors, then it goes to both. Or it goes to either one. You choose. It's up to you. Or it goes to, hey, it could go to any of them, or these two. We can't have anything like this. To be an operation, each ordered pair from the set must assign to only one thing. It must uniquely assign. And then the last sort of feature of an operation is that the operation must be closed. So let's put that word. That's an important word. Closed. So that means I can't operate on two of these and get something outside of my original set, right? Suppose I'm trying to think of a combination we don't have here. Let's say I did scissors and paper, right? And you said, well, that maps to star. So this is not closed because it brought us out of the original set. Therefore, it cannot be an operation. So in order to be an operation, each pair in the set has to go to something. Each pair in the set must go to only one thing. You can't go to multiple different things. It can't be ambiguous. And then the operation must be closed. It can only bring you to things that are in the set. It can't take you out of the set. So let's try to think of some other examples. I think for this series, we're going to take our time. We're going to go slow. Who cares if there's 200 videos? Because the idea here is let's try to understand these concepts, right? So we said uniquely defined. Let's see here. Let's come up with like a word for each of these things. Okay. So this one was, I'm forgetting. Oh yeah, so every pair. Every pair has to go to something. This was unique. And this was closed. So let's think of some examples that are like yes and no for these operations, right? So we talked about mixing colors before. So let's say we had yellow, red, and blue. So in the mixing of colors, each pair that we mix will give a color. But if we're starting with this, and we just use the way colors normally and naturally mix, this will not work because mixing this and this will give us green, which is outside of the set, so it won't be closed, right? So we can't use this set if we're using color mixing as we understand it. So we have to add some other colors in here to make this work. And we went down this rabbit hole last time. Then we discover, oh, we have to add some more here. So this set is not going to work unless it has infinite colors. That's okay. You can have an infinite set. So the set could be, set equals all colors. This would work. Every pair could be mapped to something. And let's see here. Could a specific shade or hue of blue mixed with a specific shade of yellow and give off either green or orange? Not in our normal understanding of this. So we could say they were unique too. And then, is it closed? So if we have infinite colors, then it is closed. We had to do infinite colors because when it wasn't, then it wasn't closed. So that was an important distinction to see. Let's try to think of some other examples. And I want you to think of examples and throw them in the comments. I'm never going to ask you to like and subscribe to these videos, but if you like them, or if you have questions about them, or if you hate them, or if you have ideas, anything, please throw some comments in there, because it's lonely out here on the prairie of math videos. So here we are, colors, rock, paper, scissors. Let's think about maybe a slightly mathy example, because hey, it's math. So I've got one. How about we take the maximum of the numbers, right? So let's have a set of numbers, just this, 1, 2, 3, 4, 5. And then the operation will be max. And if you've done any computer programming, you've seen this before. Max, right? 2, 3. And in this case, the max would be 3. Is this an operation? Well, let's see. Can I take every single pair here and get the max? I think I can. Now, one thing we didn't really go into with rock, paper, scissors is if you get a tie. I forgot to talk about that. So what if you have scissors, comma, scissors? What do we get there? So probably we would say draw. And that just means go again. This is sort of like an invalid thing. So this is kind of interesting. I don't know what we should say about it, but just keep in mind. The reason I thought of that was because what if I take max of 2, and 2. Well, computer program I think just does this, but these are the same. But when we're playing rock, paper, scissors, this is, player A, player B, so which one do you pick? Okay, but at any rate, so max works for every single pair, and will the result be unique? So if I take the max of 5 and 1, could I say, well, it could be 5 or 3? No, it'll always be one of the ones in there. So we'll just always end up with one number over here, and so it's unique. And then closed. Can we pick some numbers such that we get something outside of this set? Is that possible? Right? Is that possible? I say no, because if we are choosing numbers from this set, and then the operation is picking one of the pairs of, picking one of the numbers within this pair, it's going to be one of these numbers because that's where these came from. So it will be closed. And just in the last minute or 30 seconds here, let's just show you something that's not closed, just to give you an example. Let's say we take this same set here, 1, 2, 3, 4, 5, and the operation is just adding them, right? Just adding that pair. And then suppose I took 5 and 3, right? So that would map to 5 plus 3 is 8. And look, there's no A here, so this is not closed under addition. So anything you think about this, throw me a comment. I hope this was helpful. See you next time.